All right, we're doing class on a snow day. I hope you don't mind, and I'm sorry that we can't do it live, so you can't ask me questions. But please send me an email if you do have any questions about anything that I say. I hope everything's gonna make sense. Let's get to it. So we started last time talking about NFAs. Here's a quick, cute example. How about this? This is an NFA, and the way that I like to think about this is, in an NFA, you want to think about what are all the possible ways I can make it to the end, the accepting state. And the answer here is, in order to get there, you got to do an A and then a B, and then you can do whatever else you want and loop around here as much as you want. So this one accepts. You got to do an A and then a B and then anything else. So it's anything starting with AB, right? You could write it as a set if you like. It's AB X, where X is in AB star. Right? That's what this NFA accepts. Anything starting with AB. Like we said last time, NFAs often are easier than DFAs to make. Like if you want a DFA for this, it would have to be a little bit more complicated. Not super complicated, but I'm not sure you can do it in 3 states. NFA often you can do like in a more compact way than a DFA for the same thing. All right. The difference, of course, is that it can have any number of outgoing arrows from every state. It can have several with the same label on them, and it can also have missing arrows. So, for example, there's nothing from the first state which has an outgoing B. That's not allowed in a DFA, but it is allowed in a NFA. All right. There's one other thing that is allowed in an NFA, but not in a DFA that I didn't mention last time, and I'm going to mention it right now. NFAs also allow what's called a spontaneous transition. This is when the machine does a transition, like an arrow, without reading any letter from the string at all. It just does a transition just for fun, without using up any of the arrows in a string. These are also called I'm usually going to call this a epsilon transition, because when we draw it on the chart on the diagram for the NFA, it's going to be an arrow labeled with an epsilon. That indicates that you can go across this arrow, but it doesn't use up any of the letters from the string. That's called an epsilon transition. A transition without using up any letters. And you can use the epsilon transitions to do really sort of cute stuff, which is much harder to do with a DFA. For example, how about I would like a NFA for all strings. How about all strings that look like A to the N or B to the N. So that is a string which has only A's or perhaps only B's, no mixture of A's or B's. This is, it's not so hard to do on a DFA, I suppose. But here's how I would do it on an NFA. Check it out. I begin in a starting state, and I'm going to have 2 epsilons transitions, and then go right into an accepting state with A to the N's. Sorry, you can't put A to the N. It has to be just a letter. And then another accepting state with B's here. So what this means is you start here without reading any of the letters. You can either go up there or you can go down there. And then from there, you have to either do all A's or all B's. And that's how we do it. This will accept all strings that look like either all A's or all B's. All right. How about a little variation on that? Let's do the same thing. So this accepts A to the N or B to the N. How about something like I'm just going to add one extra arrow here. How about that? Put an arrow going down with an epsilon. What will be accepted now by this thing? Well, I would say it's still going to accept anything with all b's, because you can go down here and then do all the b's. All right, so b to the n is still accepted. It also still accepts a to the n, right? Because you can go up here and do a's forever, and this will accept a to the n. But there's more. You could also go up here, do some a's, and then go down here and do some b's. So it is possible to do a bunch of a's followed by a bunch of b's. But after those b's, you can't go back and do some more a's some more. All right, so this actually accepts, what is it? It could be all b's, or it could be all a's, or it could be a bunch of a's followed by a bunch of b's. Actually, we can summarize all of that just like this. A to the n, b to the m, right? Where n and m, they might be 0. So it has a certain number of a's, possibly 0 a's, followed by a certain number of b's, possibly no b's. All right, you cannot have a after a b. All right, of course, there are other ways to make an NFA, and probably actually, if I asked you to make me an NFA for this, I wouldn't expect you to do it in this way. With 3 epsilons, it's a little weird. If you knew that this was coming, there are other probably clearer ways to do this, but this will certainly work. What I wrote there with the 3 different epsilon transition. Okay. What I want to talk about for the next few minutes is the formal description of an NFA. NFA, at least in terms of its structure, is very similar to a DFA. It's just that there are like slightly different kinds of things which are allowed in an NFA. All right, so let's talk about, it's going to look pretty similar. The formal description of NFA. All right. And we're going to write this in a similar way as the DFA. It has basically 5 ingredients: the states, the alphabet, the transitions, the what comes next? The starting state, and then the set of accepting states. Those are the 5 things. And it's basically the same for NFA, although you will see that some of these things are going to be modified a little bit. But anyway, we'll get to that when it comes up. Most of it is the same. So an NFA is a 5-tuple. And I'll call it M as usual. M is, so we're still going to write this more or less the same way as much as possible. Q, sigma, delta, Q0, and F, where, and I just have to tell you what each of these things is, and I'll also tell you kind of what it represents when we think of it. Q is a finite set of states. Right? The number of states still has to be finite. That's the F. You know, it's an NFA. The F is still a F. So the Q is a finite set of states. The sigma is another finite set. And this is the alphabet. All right, the sigma also has to be finite. The delta is a function. It is the transition function. This is the most important difference, actually. Perhaps is it maybe the only difference in how we are describing these things. The delta used in an NFA has a different kind of structure from the delta used in a DFA. Maybe I will just sort of on the side here. In a DFA, if you recall, the domain and codomain of the delta is like this. Q cross sigma to Q. What that means is what you plug into the delta is a state, comma, a letter. So it looks something like, you know, delta of S comma A equals T, something like that. You plug in a single state and a letter, and what you get out is another single state. So that's the codomain here is Q because the answer is a single state. This is the principal difference in an NFA remember you can have many outgoing arrows from the same state. And so in an NFA, the answer here is not a single state, but is a set of states. So I'm going to say delta is a function. It's like this one over here, but it has a different codomain, because the answer you can get in a NFA is not just a single state, but actually a set of states. So if you have several arrows coming out, you will need more than one state to be the answer here. And remember, you could also have 0 arrows coming out, in which case this would be the empty set. So delta is a function, and it looks like this. The other, can I just say before I write it, the other difference is the delta in an NFA, it can have a letter here, but it could also have an epsilon transition, and those would be written as delta of s comma epsilon. So this part of the pair also needs to change. The second thing that you plug into delta, it may not be a letter because it might also be epsilon. So this is going to look a little messy, but here's what it has to say. Delta goes from Q cross sigma union epsilon. So what that means is the thing you plug in is a pair, where the first part of the pair is a state, that's the Q, and the second part is either a letter or epsilon, right? That's what this union here means. It could be a letter or it could be epsilon, because an NFA does allow transitions on epsilon when a DFA doesn't. And then the answer is a set of states, right? Because you can have several outgoing arrows, you're not necessarily going to get just one answer. The answer will be a set of states. And how do we write that? The answer itself will be a set. That means the codomain space here needs to be the set of all possible sets of states, right? What I write here is the set from where the answer will be taken, and the answer is itself a set of states. So what I need here is the set of all sets of states. This is complicated. I hope you remember from your discrete math class, there is actually a notation if I have a particular set S and I want to write down the set of all sets of things from S. Another way of saying that is the set of all subsets of S. That has a name that's called the power set of S. You write it with like a fancy P. That's supposed to be a fancy P. Not terribly fancy, but it's as fancy as I get. So over here, the power set of Q. All right. This is kind of complicated looking, and I'm just going to try and explain each part here. So I'll say for delta, we plug in a pair. This is what the domain represents here. We plug in a pair of a state, comma, here is a letter or epsilon, right? Epsilon doesn't count as a letter in the alphabet, but you are allowed to put an epsilon in that position when you're doing NFA, so it's like that. You use delta, you put a single state, and then followed by an individual letter or maybe epsilon. And then the answer, we plug in a pair like that. The answer, when I say what it equals, what I get over here is a set. A set of a bunch of states, all right? This is a set of states. Could be several states, could be empty if you have no answer, no arrows, all right? You get a set of states over there. All right, this, I mean, it looks kind of complicated when I try to describe it in this way, but I think it's actually not that complicated when it comes to actually writing examples. You basically do it like you write out what a DFA is formally. It's just certain things turn into sets rather than individual states as the answer. Let's just try and do an example here. Oh, sorry, we should describe all 5 ingredients, right? I sort of got bogged down in the delta, which is the most complicated thing. Let me just for the sake of completeness, fill this in. What are Q naught and F? Maybe I'll put them over here. We don't need this anymore. Q naught, just so I can fit it all on the screen at once. Q naught is the starting state. I should say, sorry. Q naught is an element of Q, right? The starting state. And the last thing, F is the set of accepting states, and just like before, it is a subset of Q. This is the set of accepting states. All right. That's a complete description of the 5 ingredients of a NFA. The only one that may give you pause is the delta. It works slightly differently from in a DFA. Everything else is the same. Let's just see. I'll draw a picture of an NFA, see if we can describe it using the formal description. So let's say, here's an example. This would be, typical easy homework problem. Easy once you know what you're doing. Let's call my first state Q1. Look at that. I learned how to draw a perfect circle with my app. You just got to be a little patient, which I'm not feeling too patient. How about this NFA? All right. Can we write down the formal description formally? It's M equals, as usual, I'm going to write in as much as I can here, but describe the delta sort of down below because that's the hard part. What comes first? The set of states, which in this case is Q1 and Q2. So it is the set Q1, Q2, comma, the alphabet. You can tell by looking at the diagram, the alphabet is A and B. So I put A and B. I don't know if you find yourself wondering, should I include epsilon there? Because as we all know, the diagram can have epsilon. Actually, I think this will become more interesting if I put in an epsilon. How about this? Let's put this middle arrow as a B and an epsilon. We don't have to change anything I wrote so far. I just wanted to indicate, make sure everybody's aware. Even if you see an epsilon up here, you don't put epsilon in here. All right. This set here is the alphabet, and epsilon does not count as an alphabet letter. Epsilon represents the empty string, the absence of a letter, but epsilon itself is not a letter. All right. Next is the delta, which, like I said, I will describe below. Comment below. And then I have to say that when it's on YouTube. Next comes the starting state, which in this example is Q1. Followed by the set of accepting states, which is just Q2, but because I have to make it a set, because in that position in the formal description, you always put a set of accepting states. All right, and now I will comment below and say, what is the delta? Where delta is, and we just have to describe, write a big list of all the possible values of delta, and here's how we do it. So the first one would be if I'm in state Q1 and I do an A, then I could do Q1 and do a B, then I could do Q1 and do an epsilon. All right. In an NFA, you need to include epsilons to say where the epsilon arrows are. Maybe there are no epsilon arrows, but you still have to indicate them. And then I will eventually fill these in. I'm going to do delta of Q2A. Each time I'm going to say what it equals, right? Delta of Q2B and delta of Q2 epsilon. Okay, so delta of Q1A. It means, where do you end up if you're in Q1 and you do an A? The answer is nowhere. There is no arrow from Q1 to anywhere with an A labeled. So this is the empty set. I'm always going to write the empty set with that sort of crossed off 0. That looks better. The empty set. All right. There are no transitions from state Q1 using an A. Okay. Delta of Q1 and B. That means, you look here, where can I get to by doing a B from state Q1? And the answer is Q2 is where you go. I say the set containing Q2. Remember, in an NFA, the answer of the transition function is always a set. It may be the empty set. It may have one thing in it. It may have more than one thing in it if you have several arrows outgoing from a particular state. All right, and delta of Q1 and epsilon. Are there any epsilon arrows? Yes, there are. Delta of Q1 and epsilon is, again, the set Q2. Because there is an epsilon transition going from Q1 to Q2. There should be a comma here. I left that out. Okay, and then the other ones, the delta of Q2. Starting from Q2, delta of Q2 and A, I look at Q2. I can do a A, I go back to Q2, and that's the only way you can do a A there. So this is the set Q2 again. Delta of Q2B is similar. If you're in Q2 and you do a B, only place you can get to is still Q2. So this is, again, the set Q2. And delta of Q2 epsilon. There is no epsilon transition from Q2. There's no arrow with an epsilon, and so that is the empty set. All right, and this is the formal description of that NFA. Any questions? I always say, any questions? You can't hear me. You must not have any questions. Comment below. All right, great. Let's talk about what it means formally to say a string is accepted. Remember, in a DFA, X is accepted means it means delta of Q0x, sorry, delta star of Q0x is an element of F, right? I want to try to work out a similar thing. I mean, is that what I just wrote? Is that actually also the way it works in an NFA, or is it a little more complicated? The answer is it's actually not exactly that, although it's the same idea. You have to write something a little more complicated. That was just a little refreshing of the memory. Maybe we should talk first about delta star, all right? For a string in an NFA, you know, delta, an individual delta, if I did something like that, is a set of possible outcomes. Could have more than one possible outcome, all right? This means that the delta star is going to be quite a bit more complicated. It means when I write delta star of, say, a state Q0 and X, for a string X, what does that mean? The idea is you start in state Q0 and you do this string X. Now, if X is a big string, there could be many, many possible places you end up after you do this string X, right? If you do a single letter, it might have several places it can go to, several outgoing arrows with that letter. If you do a whole string, there's going to be perhaps many, many different possible paths you could take through the machine. Anyway, delta star of Q0X. So what does that mean in a NFA? This is the set of all possible destinations if we start in Q0 and do the string X, all right? All possible places that you could end up, all states which are reachable from Q0 by using the string X, all right? That's what delta star is for a DFA. For an NFA. For a DFA, there's only one possible place you can end up, so it's a little simpler. But this, for an NFA, it is going to be, in general, it's going to be a big set of states. And then what does it mean to be accepted? Remember we said last time, X is accepted if any of the possible destinations is an accepting state. So X is accepted if any of these destinations is an accepting state. That is, if any state in delta star Q0 X is in F, right? That's what it means to be accepted, is if any of the states in there is an element of F. So another way you could write this is L of M. That is the language of the NFA. It is the set of all X in sigma star, all strings, such that delta star of Q0 and X contains an element of F. This is a set, right? To say it's accepted, it means when you look at that delta star thing, that tells you all the possible destinations. One of those is accepting, then X is accepted. Actually, there's a fancy way to write that. I hope that makes sense in words. There's a fancier way to write this if you want to look fancy in front of your friends. In front of your friends and their moms. You can write it this way. How about this? Delta star Q0X intersect F is not the empty set. All right. How you like that? Is not the empty set. That means there is some element of this set. This intersection does contain something, and that something must be a state in here, which is also part of F. So that's equivalent to saying it this way. This contains an element of F is equivalent to saying that thing intersect F is not the empty set. All right, great. And this is what we're going to take to be the definition of the language of the machine. It's all the strings which obey that somewhat weird-looking formula there. It looks complicated. It's not really much more complicated than for DFAs. It's just that everything is sets rather than individual states, so you have to say things in a slightly more convoluted way. All right. I want to talk about one thing that's really nice about NFAs is that you can easily combine together NFA diagrams to accept different languages. Now, we saw for DFAs, you can do, you can take the complement very easily with a DFA. You can also do the intersection of two languages on DFAs, although that I would say is not terribly easy. You have to do that product thing, which is, you make a new DFA which has a bunch of pairs, and then you have to sort of carefully decide where all the arrows go. The product construction for DFAs is what you use to get the intersection and also the union. NFAs are actually quite a bit easier to patch together to get unions, at least. It's actually not very easy to do intersections on an NFA, but on if you want unions, it is quite easy to do. So let's talk about unions with NFA. There's a simple construction, much easier than doing that product thing that we did last time. A simple construction by which you can combine together two NFAs to get the union language. So, for example, let's say I have one NFA, which is like this. This is kind of like that one that we were just talking about formally. Let's say that's M1, and then let's say this is M2. B. How about that? All right, I have two NFAs. And what is the language of each of those? These are fairly straightforward. The language of M1, when you look at the diagram, you should ask yourself, what are all the possible ways that I could get to the accepting state? And in this case, you have to do a B first, and then you can do a whole bunch of whatever you want. So the language of this is anything that starts with a B. I could write BX, such that X is any string on AB, right? Anything that starts with a B. And then the second one, actually, that would be anything that ends with a B, right? Again, I asked myself, how can I possibly get to the accepting state? And the answer is, you can do whatever you want for a while, but then you got to do a B, and that's how you end up in the accepting state. So this one, the language of M2 is actually XB, right? This would be all strings which end with a B, all right? Now, can we put them together with the word or, all right? That's what I'm talking about with the unions. So an NFA for L of M1 union L of M2, all right? This would be everything that starts with a B or ends with B, right? anything that starts with a B or ends with a B. How would we do that? There's a very simple sort of little trick you can do to get or on an NFA. Here's what we do. We start with sort of a dummy state, which is the starting state. And then I'm going to put, this is actually similar to an example I talked about a little bit ago. I put 2 epsilon transitions, and they each plug into the starting states of M1 and M2. So this one, I am just going to fill in M1 exactly as it appeared before. So like what you see right here is actually M1, right? And then I'm going to plug into the second branch down here, M2. What you see down here is M2, all right? And this is how you combine 2 NFAs to get the union. All you got to do is this same sort of little pattern here. So I am going to, and I hope you can see why this gives you the union, because you have to start here, and immediately you either decide to go up there or you decide to go down there. And the fact that I just said the word "or" is why you get the union. In order to be accepted in this big machine, you have to either be accepted up here or you have to be accepted down here, all right? This is why what you get for the language is the union of the original 2 languages. So generally speaking, if we have 2 machines, doesn't matter what they look like, M1 and M2, to get the language of M1 union the language of M2, what you do is this. You start with some starting state. You do 2 epsilon transitions, and then you sort of plug into M1 here, and you plug into M2 here. By plug in, I mean you make this epsilon transition point at the starting state of M1, and then you make this other epsilon transition point at the starting state of M2. All right, this is how you plug together 2 NFAs and get the union. There is nothing, there's no comparable sort of simple, cute way to plug together 2 DFAs, because this requires epsilon transitions, and you can't really do that in a convenient way with a DFA. All right. There are other, you might imagine many different ways that you could think of plugging one NFA and another NFA together into a bigger machine. This is sort of, I would describe this as hooking them up in parallel. This is like how an electrical engineer would describe this. You could hook these things up in parallel. You could also think about hooking them up in series. Does that give you anything interesting? Actually, it does. So what if we did, so rather than parallel, meaning you do like 2 branching paths and then the one on the one side, the other on the other side. In series would be more like you do 1 first and then you pipe that directly into the second one second. So what do we get? And is it useful for anything? Actually, it is. What do we get from something like this? What if I just make my starting state, have an epsilon straight into M1, and then from there you continue, I'll just put another epsilon, meaning once you're done with M1, you shove it through M2 and then see what happens. Is this actually useful for anything? And can we describe this in terms of unions or whatever? This one gives you the union. It's natural to think, well, the one that goes with that is the intersection. But actually, this construction here does not give you the intersection of the 2 languages. Think about what does it mean to get all the way to the end of M2 and finally be accepted here. It means you have a string which was accepted on M1, and then that string is immediately followed by another string which is accepted on M2. So this one accepts strings of this form, strings that look like XY, where X is in the language of M1 and Y is in the language of M2, right? It is going to accept a string which is made up of like the first part of the string got you all the way through M1 and when it was accepted. And then the second part of the string, which is the Y, is accepted on the second part of the machine. So for example, in like this case up here, we had starts with B. Our two machines were starting with B and ending with B. Maybe I'll do a little copy paste action here. Sorry, I know this is hard for you to do on your paper. What does it look like when we do this to those that stuff? This says you do B, and then you can do, so M1 says you start with a B, and then you can do anything you want. That's M1, and then I want to follow that immediately by M2. So the way I would actually build this machine would be, I start with sort of the entryway state, followed by an epsilon that ties into the starting state of M1. Sorry, in my combined state, I'm not making that an accepting state. That's because I'm not actually done yet. You know, my intention is to tie them together like you see up there. I do the first machine first. This is the M1. And then I'm going to send the output of that, immediately make it go through M2 also. So I'm going to put an epsilon here into the starting state of M2, which is this guy. And then finally, it will be accepted over here. This is the M2, all right? This is how you would have to tie together two machines like this. You make what used to be the accepting state here. It's not an accepting state anymore, but it epsilons over to the next one. All right. In this particular example, I had only one accepting state. In more generality, you could have several accepting states. You would put them all here and make epsilons go from all of those accepting states into the starting state of the next machine. All right. Anyway, what does this mean in terms of the language? It gives you things a string which you can break down into two pieces. The first piece is accepting on the first machine. The second piece is accepting on the second machine. There's actually a name for that. This gives the concatenation of the two languages. Concatenation of the languages. And it's written like this: L of M1, L of M2. So there's not a operation symbol that we use for that. You just write the two languages next to each other: L of M1, L of M2. What that means is all the things which are part of the first language followed immediately by things which are part of the second language. So as a set, the definition is it's all XY such that X is in L of M1 and Y is in L of M2. That's the meaning of this thing over here. There's no operation right there. It's just, there's no, we don't write an operation there. L of M1 followed by L of M2. All right. You can actually, this is, the way I've been saying it is kind of like just sort of playing games with the diagrams, but actually you can use this as a general approach for helping you to draw the NFA for fairly complicated languages. For example, so to draw a complicated, well, what I mean is to draw the NFA for a complicated language. Delete. To draw the NFA for a complicated language. This doesn't always work, but sometimes it's helpful. I'll say maybe think of it as a union. All right. And then tie it all together as a union. So for example, here's this is a typical sort of homework style problem. How about make an NFA which accepts any string with even length or an even number of B's. Even length or an even number of B's. All right. That is a hard kind of thing to even think about, even length or an even number of B's. Of course, many things which are even length would have an even number of B's, but not all. And it's a weird set. But I see this magic word or. That means I can think of this instead as a union. So when I say even length or even number of B's, I'm going to think of it as a union. Think of it like a union. There's one set which would be even length, and then union with a set which is even number of B's. Right? And so I'm going to make an NFA for each of those two things and then patch them together with that simple sort of in parallel epsilons construction, and then we'll have a machine that gives me the union. So let's do each of these. Let's call this one M1 and M2, right? I'll call that M1 and I'll call that M2. Really, these are the languages of M1 and L of M2. How do we draw a machine which gives accepts with even length? Actually, this is very easy to do even for as a DFA. Whenever I see evens odds, I think of arrows going back and forth. To get any string of any even length, that means I don't care if there's A's or B's or whatever. All I care is how many individual letters. So I'm just going back and forth. Every letter sends me back and forth. All right. That's a DFA, but it also still counts as an NFA, right? So if I ever ask you to make an NFA to do something or other, you could make a DFA, and that's still a valid answer. So this is an NFA for even lengths. And then how about NFA for an even number of B's? This also is most convenient to just use a DFA. An even number of B's would be like this, but just with B's there, and then looped A's like that. All right. I go back and forth every time I see a B, and I don't care about the A's. When you see A's, it doesn't affect the states at all. All right. My final answer, remember, is meant to be the first thing or the second thing. So my final answer then is going to be this. And this is just a useful pattern that you should remember whenever I want to combine two NFAs with an or a union. This is how we do it. We send epsilons going in two different parallel paths. So up top, I put the first machine, and on the bottom, I put the second machine. There we are. This is my final answer. So the moral of the story is, sometimes if you're asked to make an NFA for a weird set, a weird language, you can break that set down as a union or maybe as a concatenation and then patch together smaller, simpler NFAs into a big one. All right. And I think that's going to do it for today. We were supposed to have a quiz today anyway, so I'm not going to go the full 50 minutes. So I will leave it at that. Thank you for your attention. See you next time.